Awesome. Welcome, everyone. This is Deep Learning Adventures, and I'm so happy to see so many new friends and existing friends, and thank you again for joining us. My name is George, and let me share my screen real quick so that you have a better idea of our meetup and what we do. You can find us on Meetup if you search for Deep Learning Adventures. We started this journey back in April, actually, and I'm amazed and surprised by the amazing growth of our community and our I like to believe strong bond among us. So thank you for joining us. We have about 900 members so far, and we're growing strong. Today, we're going to talk a little bit about geospatial analysis. Me and Kathleen, my great friend Kathleen, will talk about that. I'm joined today by my great colleagues and co-organizers, David and Robert, and as well as many friends from around the country and around the world. So welcome, everyone. Just some housekeeping. Next week, we're going to have a happy hour on Wednesday. And the goal was to just have another session on Friday, but I heard many of my friends say, what are you doing for Thanksgiving? It would be nice to do something. So actually, we're hosting what is called a Friendsgiving, which is basically a happy hour with maybe a drink or food if you want. I'm hoping to have something planned for us in terms of surprise, so check it out as well. I'm asking some of our great friends to help us out with the surprise part, but it should be fun. We've done so many things together, and I think it's a good opportunity for us to get together and just get to know each other better. Cool. That said, all our sessions are recorded, and I'll post a link right now in the chat. As you've seen, we've been pretty busy with this Kaggle series. We have done sessions on Python, introduction to machine learning, data visualization, feature engineering, SQL, data cleaning. And today we're going to talk about geospatial analysis. So before I do that, let me just share some links on the chat so that you can join us on Slack, as well as you can find our previous recordings. Awesome. So I'll be talking about the first three sections of this part, creating a first map, the coordinate reference systems, and interactive maps. And Kathleen will talk about some more advanced geospatial analysis topics. Okay, let's take our first step. Let me zoom in a little bit. So far we've seen structured data. Most of our data has been handled with pandas, and we've seen basically tables. We've seen how to work with indexes, how to work with features, how to work with columns, how to do different group by operations, how to do different joins, either in pandas or SQL. And pretty much our data has been well structured, and you can visualize it by just looking at a table. So today we're going to talk a little bit about data that have a geospatial characteristic to them. That means that they have a latitude or a longitude or some kind of a line or a shape feature attached to them. And some cool projects that we're going to look along. We're going to look at a global nonprofit called Kiva. We'll be looking at how they could expand their reach in remote areas, for example, in the Philippines. A specific bird type, a purple martin, which is a threatened bird species. We'll analyze together how they travel between North and South America, and are they going to conservation areas or not. Then we'll look at another data set from Japan that, Japan is close to two tectonic plates and is very earthquake prone. So we're going to look at some areas there and which densely populated areas could use earthquake reinforcement. And some other data sets that hopefully Kathleen will take a deeper dive. For example, in California, what are some good candidate locations for a new Starbucks store, in case we don't have enough of them, as well as New York City for coverage from a nearby hospital. Cool. So we'll start with a new library for us in this Kaggle series. We've seen pandas. We're going to start with another extended version of pandas, which is called GeoPandas. And we'll import that as GPD. This is a great library for us to read different geospatial file formats, and some of them are shapefile, GeoJSON, KML, and so forth. And I just wanted to show you an example of, for example, GeoJSON, how it looks like here. So it looks like a very structured data set. You can see here you have a feature collection, which is basically a collection of different features, and then a list, think of it that way, or a dictionary. Within that, we have different types. In this case, we just have one feature. That feature is made up of a single point here, and that's the coordinates of that point. We can have something else. We can have like a collection of points which make up a line string, or we can have a polygon which they make a line string, but then the last and the first item is the same, if you see here. Okay, let me go back. So to start looking at some real-world data, we'll look at the Department of Environmental Conservation in New York State. And we're going to look at data and information about forest, wilderness, and other land. So this data is available for this notebook in this repository or in this specific path. And if you notice, it's a shapefile. Anything that ends with SHB, that's a shapefile which describes how a region is encoded. So similar to pandas, we can do so now this is a GeoPandas object or data frame. We can do a head method to look at the first few records, and you can see we have an object ID, a category, a unit, a facility, a class, description, region, country, URL, office, acres, shape area, and then geometry is the main column that we'll be interested in, because that will allow us to visualize our locations. Okay, so we look at the type of this object, and you can see that's a GeoPandas geodata frame type. It has similar methods and similar access features as a panda. So for example, we could do the location feature that we are used to in pandas. And this means give me all the rows. That's why they have usually the semicolon, but only give me these 3 columns instead of all of them, and just create a copy of all the data and save it in this new data frame called data. So basically I'm interested in all the rows, but only 3 columns out of, I don't know how many columns are here. Let's say 20, 30. We can also use, for example, class is a specific feature that we're interested in. We can access that using the dot operator, and then as well as the method value counts, which will give us basically a histogram of the different values. So for example, wild forest is used 965 times in this data frame, intensive use 108, primitive, wilderness, unclassified, and so forth. So we create another data frame from our first main data set, looking only at wild forest and wilderness. We store that under wildlands. And if you see, we have a class, a county, and a geometry. Then let's create our first map. So far we have 3 columns, and we also have a geometry field. That's the most important part. This is a GeoPandas data frame, so it has a built-in method called plot. And if we look at that, let me zoom in a little bit more. It looks like a visualization, it looks like a map, but there's nothing in the background that helps us to visualize it or understand what are we looking at. So let's see how can we improve on this, and how can we get a better understanding of this geospatial data. So that's the geometry field. We're just looking at the first few records, and then this is just an introduction of what kind of objects could this geometry field be made up of. So it could be a single point, like this is an example here of a single point. It could be what is called a line string, which is a collection of points, and the order matters. Or it could be a polygon where you start, again, similar to a line string, but you end up where you started, and that defines also an inner area inside the polygon or an outer area outside the polygon. In this case, we see 3 polygons: the bigger one, the triangle one, and the quadrilateral one. So you can have as many polygons as you want, and they cannot intersect, they can overlap, they can be independent. Okay, so let's look at, we will look at campsite locations, and we'll visualize them as points because they have exact latitude and longitude. We'll look at some food trails. So this is a collection of data points. We'll encode them with a line string. We'll also look at some county boundaries to see where all does this geographical information belong to. So we'll use polygons for that. Great. So let's read, first of all, some new data for us. Let's look at the another data file for point of interest. This looks like the campsites. It's a shape file. We are only interested in a subset of that file, that the feature asset is equal to primitive campsite. So we download all the data. We only filter out the specific asset. We store the resulting data in this geodata frame called campsites. Then we look at the food trails, and that's in another input file for us called here road trails. We only interested in food trails in terms of the asset category. And for the boundaries, we are just going to use the entire boundaries. We don't do any filtering here. It looks like this already filtered for New York State county boundaries. Okay, let's look at how easy it is to create a map using GeoPandas. So we will start with the counties. We will call the method plot here. We can specify how wide or tall our map will be, and if we're going to use a specific color overall, as well as the edges of each region, and what color do you want to assign. On top of that, we'll overlay the wildlands, which was, if you remember, the different areas where forest information is stored, campsites, the exact latitude, longitude information of each campsite, as well as trails, which was encoded with a line string. We're going to assign some different colors. So now this combination of visualizations, we get something like this. And to decode this, the county's shapefile gave us, as you can see here, the different background map that you see here. Then in green, we have the wildlands, as you can see here. In maroon, we have the campsites, and in black, we have the different trails. So it looks like there's a lot of activity here in upstate New York, basically. You can see that. Cool. So that was our first adventure in just making a very simple map. You notice that we had to rely a lot on the geometry class, and we'll see that again. And we came across this new data types or under geodata frames of line string, a point, line string, and polygon. Let me know if you have any feedback, comments, questions. Feel free to unmute yourself or post them in the chat.
Yeah, the axes, the units on the axes, you would expect it to be latitude and longitude.
Yeah, that's a good point. They're not. Yeah, we'll look at some other more advanced visualization maps. I'm not sure what the X and Y axis here. That's a good observation.
Does LE6 mean 5 to the 6?
1 E6,
10 to the,
I think.
What's that?
I think that's 1 E6, like 1 times 10
Yeah,
to the
10 to
6.
the power 6. So
Yeah, so it's be 5 million.
4 million. Yeah.
It's distance in meters, maybe?
Yeah, they're in meters. UTM, I think, is the name of the coordinate. But I'm not sure why it plotted them with that coordinate here, because I thought I saw lat and lon in the polygon object above.
Let's go back up and look at it.
Yeah, we didn't specify the coordinate system, as we'll see soon. So maybe by default.
You do. Oh, yeah.
That system is just something that by default plots this way.
Yeah, we didn't specify it here, and we just read it from the file. So good observation. Go ahead, Kathleen.
Can you scroll up to the a head file? You know, a head display where it shows a few of the records?
Yeah, I'll do that in the exercise.
Okay.
Yeah. Cool. So let's look at our first exercise where you can interact with the data. So for this exercise, we'll look at a data set from Kiva.org, which is an online crowdsourcing platform where you can lend money to people around the world. And so far, this organization has loaned over $1 billion to loans to over 2 million people. So interesting very interesting platform. You can check it out if you visit kiva.org here. So we'll look at the way that their business model is. They work with what is called a field partner. So there could be a local organization, and they do basically kind of, I would say, the heavy lifting of vetting the borrowers, providing services, and administering the loans. So we'll look at a specific part of the world that Kiva is working on, Philippines, and we'll look at their coverage, and basically we're going to look at where could they expand their current network in order to give more opportunities to field partners. If you've come across Kaggle notebooks before, or Kaggle exercises, there's some boilerplate template or imports that you need to use just to get some feedback in case you get stuck in the exercises. But for coding purposes, the main library that we're going to use is this GeoPandas as GPD. Then we'll look at this Kiva loans.shapefile, and let's take a look at it and see how it looks like. Right here. So we have a partner ID field, we have a field part, let me get it bigger. We have a sector, a loan theme, could be higher education, vulnerable population, sanitation, country, amount, and most importantly, geometry, which in this case looks like a lat long, a point. Next, we're going to use what is called in GeoPandas this natural earth low resolution background. We'll just look at that. So that has information for each country in the world, like estimated population, continent, the name of the country, ISO code for that country, the GDP for that country, and the geometry, which in this case could be a multi-polygon or a polygon. So then we want to plot our world data set first, which contains basically the shapefile of each country. And on top of that, we also want to plot our loan information, which is a latitude and longitude information. All right, so this is our first map. So the light grayish lines that you see, that's coming from the world Earth low resolution shapefile, and all the green data points are coming from the Kiva's field partner network. So you can see here they have basically global coverage. Okay, now let's look at we want to filter for loans based in the Philippines. So let's see how we're going to do that. So as a reminder, this is our data set, and we have a country field here that hopefully we can use to filter for a specific country. And again, we do that using a similar syntax to Pandas. So we do a dot location, and then we filter for only the country field where its value matches Philippines. We create a new data frame. We save it under Philippines loans. And we look at the first few records. Now, they look similar to the data frame before, it's just that we filter now for a specific country. Great. So now let's work with a shapefile or a geospatial file that is more focused towards the specific country we're interested in this case, Philippines. So we will use a slightly different format, this KML format that is specifically to the country of Philippines. Let's look at first few records as well. These are human readable. So we have a name, which looks like a region name or a city, I'm not sure. And then we have a geometry, which is basically an area. Great, so now we have our area location. We will plot that in a 20 by 20 map. Just give it a light gray background, or in this case, a dark or what is called a white smoke color. You'll see that how it looks. On top of that, we're going to visualize our loans in light green. There you go. So this is just looking at the Philippines, the specific country. And you see it's made up of so many islands. And you see the northern part, there's more activity, in the central part as well. And then the southern part, there's not a lot of activity. The next question is going to ask us to give some feedback on the different regions. And I have a map here for what is basically different regions in the country. And also I was able to get some information about population density for each, what is called province. So we're going to use both this information soon to do some analysis for us. So the darker the color here, the more densely populated that area is. So the question is, can you identify any islands where it might be useful to recruit new field partners? And that's, they refer to this map here, which is basically a breakdown of the regions in the Philippines. So I guess looking at this map, what are some areas we could focus on? So maybe this area here, there's not a lot of interest. I mean, there's not a lot of activity. Let's see if that is densely populated or not, though. Somehow, yeah, it's not super dense, but it's not super sparse either. So maybe that'll be a good area. And to figure out, the names, you can refer to this map here. I found this interesting. We're going to look at some more examples later on that actually calculate the population density or how many data points we have for inside each polygon, so we can get some more exact answers. That was our first exercise.
Yeah, I think it's very helpful to look at the density when answering a question like that. It surprises me how many visualizations I see of things like coronavirus cases by county, which don't normalize for county population. So it's not surprising that the ones where all the people live are the ones with all the cases too.
Yep. Awesome. Let me turn this off. And let's go to our second part, the coordinate reference system. So the challenge in this notebook is that, so this is more of a generic challenge, but there's no perfect way to map all the points in our globe to a flat area. I mean, that's just a mathematical certainty, like simply because they belong to a sphere. No matter if you want to visualize it on a plane or two-dimensional plane, your area or some other metric will be distorted. That's why we use what is called a map projection to convert a point that is on the globe to a plane that we can visualize on a two-dimensional. But when we do that, there are so many different map projections that you can work with. Something will be distorted. It could be the distance between 2 points. It could be the area of a region. It could be an angle between two different data points, and so forth. So none of the map projections are 100% accurate. Basically, that's the key takeaway. There are some of them that try to give emphasis on different metrics. So for example, equal area projection, like for example, I have another visualization here. Like this one here, we'll try to keep the size or the area the same. And you can see here, South America, Africa, Australia. There are some other ones that will give probably importance to the distance between points, some other ones between the angles. I think the one that we use give more importance to the angles, simply because it was used for in the older times when different ships used to navigate. It was very important for them to figure out the angle between two data points so that they could actually reach their destination safely. They didn't care as much about representing in the area, I guess, as accurate as possible. There's some other projections that want to make sure that the distance between 2 points is preserved as closely as possible on the globe when mapped on a plane. For us, we're going to use different what is called the coordinate reference systems, and that basically show how the how we project points from the globe to a plane, to a two-dimensional surface. So how do we set this, and what is the impact of it? Let's take a look. We're going to read a file here from Ghana, from Africa, Ghana, and we're going to look at the CRS feature, and you'll see something called Epsg, which is the European Petroleum Survey Group codes. And if we look at that page, I think it's this one. Yep. We'll see some information about what is their meridian. So where does it start? In this case, Greenwich. When was it created? 1995. Where is it used? And you have some locations here. And what is the unit? This is very important. It's in meters. So this is also called the Mercator Projection. It preserves angles, making it useful for sea navigation, and slightly distorts the area. So another thing we're going to do is we're going to look at health facilities, and hopefully they have some kind of a geospatial information in them. So let's take a look. So it looks like, yeah, they have a latitude and longitude. We're going to use from GeoPandas, we're going to create a new GeoPandas data frame using this CSV file. And this CSV file has two fields, latitude and longitude. We're going to use a method from GeoPandas called points from XY that will basically create a geometry object out of latitude and longitude fields in the CSV file. We'll also specify the coordinate reference system, the CRS, to another one. And we're going to look at the first few records. So all these fields that we're looking at: region, district, facility name, type, clinic, health center, town, ownership, latitude, longitude, are there in the existing CSV file. This is the only new field that we created, this geometry field, using this points from XY. We can use other reference systems. So this is us visualizing that data using this 32630 coordinate system, just using the regions.plot method. And this is how it looks like. So I want to make sure. So the original one was 4326, but we used another one for visualization. And you can do that on the fly, as you can see here. You can do facilities, you can change the projection system on the fly before you call plot. And yep, that's few records. You can use other ones as well. I'm not sure when you'd use this. In this case, it says, in the case where this code is not available in GeoPandas, you can use a string construct. There's a short description here. I don't think we're going to use this in detail. So this looks more like a custom projection than maybe the one that's already defined in GeoPandas. Great, so if we have a geometry object, we can look at the X, or the coordinate of each point. We can also look at the area. There's a field called area, which gives you the area of a region. We can also sum up the total area of multiple regions using the area field and using this operator sum here. So first of all, we create a new field called area, as they're looking at the geometry field, and using this attribute area, we divide that by 10 to the power 6 to convert it to square meters. Then we add up for all the regions, what is this area in square kilometers. We also print out the CRS. So if we see here, the area of Ghana is 239,000 square kilometers. And the CRS we use is this Epsg 32630. We can look at the area for each in the different regions. And I think here, there's just a quick discussion of the correct answer. So we came up with this number, 239,584, and the correct answer is I don't want it in miles.
It's just below it. in the link below.
That's Nigeria, Mali, Kenya.
It's 240,000 if you look at the second link below.
Oh, there you go. 239,540. 239,540. We got 239,584. So almost there. Again, that's the difference in the projection that we're using. We were using one that was not giving emphasis on not distorting the area much. Cool. I'd like to go to the exercise. Let me know if there's any questions about this. This was an interesting topic. Okay, then we'll look at a new data set. We'll look at this data set that is tracking migration patterns for this beautiful bird, this purple martin. And in the summer, they usually in the east or middle part of the US, and in the winter, they go down to South America for holidays. So let's see how they look like, and how does this travel look like. We'll also look at what is called a protected area in South America. Ideally want to make sure that all the birds, when they migrate, they go somewhere nearby a protected area. And I have a map here of different protected areas around the world. In green, they're terrestrial, and in blue, they're marine on the water. Great. So let's look at this new data set and how it looks like. We're going to need pandas and GeoPandas to work with. We're going to need this line string just to plot some visualizations of the different migration lines as well. Then we'll look at this purple martin CSV. It has a timestamp and some other fields. And let's see how many unique birds we have and how does this data look like. So if we're looking at the structure of this data set, we have a timestamp, we have a latitude, longitude, and then we have what is called an identifier. This is identifier for the bird. And if we look at this method, n-unique will give us the unique number of birds in this data set. And if you can see here, we only have 11. So there's 11 unique birds. The next thing is, let's create, this is a CSV file. So we need to create this geometry. There's no geometry field here. So we need to create it if we want to visualize this data better. So we created calling these points from XY that we saw above. We need to specify the longitude and latitude in this specific order. And our main data set is this bird's data frame. We can also specify the CRS. And then we can start visualizing the data. We'll use the natural low resolution. We'll focus in North and South America. Let's see how that looks like. So that's, again, some basic information about each country. And most importantly, this region or geometry field that we need. Just a reminder here that latitudes start with 0 at the equator. And then we have a northern and the southern one. And if you go up, you can go from 0 degrees all the way to 90, or from 0 degrees all the way to 90 south if you go south part of it. Then the longitude for our projection, the first or the 0th longitude will be on Greenwich. And then we have a west and east, depending on where you go, if you go right or left. Okay, so we're going to look at the background of each country. On top of that, we will plot our locations of our birds, basically. And you see here we have in blue the location of the birds. Probably in the US is where they spend their time during the summer, and then in the South America is probably where they spend their time during the winter for us. Let's actually visualize their journey. So this is our points. We can, for each bird, we can actually group their multiple points into a list. And let's see, how do we do that? So we've seen the group by method before in Pandas. I'm only looking at the first 30 records here. I'm grouping by this identifier. So basically I'm grouping by each bird, and I'm looking at the geometry. And I'm applying what is called this list method. Apply takes a function as input. And I'm applying this list method. So what that will do is for each bird, it will give me a list of points. And hopefully that's the journey of the bird. Furthermore, I can apply what is called this line string constructor that is basically better suited for us to visualize it using GeoPandas. So now from point, we went to line string. So we can do all that with this command here. So a little bit more. And then in the end, we can do this reset index to basically reset this index that you see here. Then we can create a new geodata frame file using this path data frame, the geometries, the geometry, the existing one. We can look at the first few records. So now we have a bird and a collection of data points or a line string. We can do the same for, we want to extract the very first location of the bird. So we do that using this geometry field again, but we're only interested in the very first item of that list. So basically that would be our starting point when a bird migrates. And we can do the same for what is called the endpoint. So we're going to look at x-1. That's the last item for each bird in this geometry field. Great, so now we have the country information, the region information. We have our path as line strings. We have our starting point, and we have our ending point. And I'm just assigning different colors here so that I can see them better. And a nice thing in GeoPandas, you can also specify the X limit and the Y limit, so you can focus on different latitude and longitude here instead of looking at the global map. Let me zoom out a little bit. So in blue, if you remember, I assigned the starting point, and in orange, the end point. So as you can see, blue is over here and orange is over here. And then different lines connect basically different data points and different colors for different birds, as you can see here. So
George, how did you, what's the command that you got the different colors for the different lines?
That's not a specific, yeah, that's what is called a collection of map, a C map, and it's using this 20 different colors. So instead of color, you give C map.
It just randomly assigns it to the.
Yeah, I think it's made up of 20 colors, and it will just pick. It will start from the first one to the last one.
Good. Okay.
Yeah, it was easier to read than just assigning the same color to different lines. Cool. Next question is: we know that the birds are migrating south. Are they going to what is called a protected area or not? So we're going to read this shapefile, which contains the protected areas in South America. I'm going to look at a few records, see how it looks like. It's a big file. So we have a lot of information here. 29 columns. I'm just looking at the first 5 rows. Some ID for each area, protected area, a name, Arikok National Park, maybe designation, some other information, definitely the country or the city or the area nearby, which we're not visualizing here. If it's verified by the state, and a geometry. What it looks like it's a polygon or multi-polygon. So how does it look like if we visualize it on a map? Great, so now we're going to take our background map. We're going to focus only on the Southern American part. And on top of that, we will plot these protected areas that we saw above. This alpha parameter will just make our colors a little bit dimmer so that they don't overwhelm the continent background. Great, so we have the background in gray, and then in blue, we have the protected areas. They could be on the ground, or it can be on the sea here, as you can see. Zoom out a little bit more. I'm just focusing on South America here. all the way to Argentina, all the way to the southern pole. Great. Now, the question would be, what percentage of South America is actually protected? And from our protected area data frame, we're only going to take out of 29 columns, we're only going to take a subset of them. This is me just looking around. I'm interested in this area here. And we have our protected area, rep area. Looks like it's the area is, I think the unit is in square kilometers. Yep. Oh, the marine one. We're going to remove the marine protected areas. We're only interested in protected areas on the ground here. Then let's see what is the total area of the entire continent. So we have a South America data frame. We can access the geometry field, and that geometry field also has an attribute called area, and we can divide by 10 to the 6 so we can convert it to square kilometers. So we do that for all of them. We also set the CRS to 3035, and we look at the area field and we add a sum, and it didn't give me the total area. So that's the total area of the entire South American continent. And let's now do a simple ratio here of the protected versus the entire region. So 30% of the entire South American continent is actually protected, under protected area, which is very interesting. Then next we're going to look at what happened to our birds and if they're actually going to a protected area or not. We will exclude the marine part. We'll visualize the path as well as the starting and end point and the protected area as well. So using this axis, that's the key takeaway here is that using this axis when we create the first plot, using any subsequent plots, make sure that we're overlaying our maps on the same region. We can also zoom in, zoom out a little bit here based on latitude and longitude. So this should give us the protected areas, the starting point, the ending point of the bird migration, as well as their path. And I zoomed in specifically in the southern part of the map here. So if it's blue, that means that it's a protected area. So let's see this red bird here. It's flying around, eventually landing in this protected area here. Same with this one. This one doesn't seem so. This one is very close to one, and so forth. Let's look at another visualization. I think this was one that the notebook had.
George, a question. Did you see anywhere how they figure out which order the points turn into, what they use for a line?
I think it was in the order that they appear in the data set. So I'm hoping that there's a timestamp information there. So maybe it was sorted by time. But then as you create this line string, you basically do them over time.
There was a timestamp there.
Yep.
Okay.
And this is what the notebook had. I'm trying to figure out why the notebook has way more data points than my visualization, and I still haven't figured that out. But in red is basically the bird's location, and in blue is where if it's a protected area or not. And you can see most of them looks like they're going to a protected area, except for this guy's here maybe.
I think it has more because it's showing all the flight path points, right? It's not showing just the end.
Oh, I see. So this are in between then, you're saying?
Yeah. So this, I think that's, if you look back at yours, you'll see.
Yeah.
This
Yep, right here. Yeah.
right.
Yeah.
So I'm actually not putting a dot on every point.
You're just putting the end.
Got it.
And they're showing all the points.
Okay. So maybe he took a quick break here and then eventually ended up there. I don't know. That's interesting. Thank you, David. Cool. I like this. This was really cool. Any comments or feedback here?
I just think it's amazing how much you can do with so few lines of code.
3 lines, right? Yeah, yeah. As long as your data is properly structured, right?
Yeah, that's always the case.
Yeah. You can, like this, you can also zoom in and zoom out as much as you want here. Let's make this 40 maybe.
You know, one other thing I run into a lot with these kind of things is, especially if you're working with like satellite images and things, is I mean, this data runs inside a nice Kaggle notebook, but sometimes the file sizes can be just gigantic.
Oh yeah.
And so slicing and dicing is very important to get them down to a reasonable size.
Awesome.
Yeah, that last map looks like a fly in a straight line. As the crow flies, so to speak.
It's the marlin flies. Martin, the purple martin.
Purple mark. All right.
It's not as funny as crow.
We'll look at a new package in this interactive maps section. It's called Folium. It's really impressive, really user-friendly, and really developer-friendly, I would say. So it's a new package from Python. The documentation is not the best, but for the things that we're going to visualize, all we need to know is the name, the package name, as well as some different classes that we're going to use. So we're going to use a package called choropleth, circle, marker, as well as from different plugins. We're going to use a heat map and a cluster of different markers. So how easy to use this new package? You can just use folium.map. You can give a specific latitude, longitude, or location. You have to specify what is called the background map. In this case, we're using OpenStreetMap. And the zoom start is just a number that the higher it is, the more zoomed in you are. And the lower it is, the more zoomed out you are. So just doing that and just displaying it, you can see here we have a live map that is focused around Boston. And you can zoom out, you can go anywhere in the world. Let's go to a tiny little country called Albania right here. A good friend of mine is from there. I mean, me.
Where are you from?
Let's go to I'm here in the southern part. Right here, this is my village right here, Malic.
Wow.
There's a little lake there. This is my soccer field. I used to run in this soccer field all the time. This is my school.
Wow.
It'd be nice if this was like maybe satellite. This, I used to go for vacation. There's a huge lake here. And the northern part is known for like what is called like the Alps. And the western part is Italy. So it's a Mediterranean. So it's beautiful and full with sun. All right. Let's go to the next one. So we had a center for our map, which was the city of Boston. We used the OpenStreetMap. You can use other maps as well here. Let me see. So we used OpenStreet. We can use maybe terrain, watercolor. I'm not sure. Each one of them probably looks slightly different, and maybe it's for different applications. And again, the higher the zoom is, the closer into the map you are. Cool. So let's look at some data. We're going to look at some crime data here, and we'll import them from this crimesinboston.csv file. We will drop any record where the latitude and longitude is not there. So drop NA, and in drop NA you can specify a subset, which is a list, and also in place true, meaning do these changes and update the underlying data frame as well. For the entire data set, we're only going to filter for some offensive code groups, what is called offense code groups, and those are these ones here. And we're also going to look at reports that have taken place or incidents after 2018. So after doing all this filtering, we have an incident number, a code, a group, a description, a district of the city, reporting area, the date, year, month, day of the year, hour, street. Latitude and longitude is very important for us, and location, which is a combination of both. So for our first map, we're only going to look at robberies. So in our crimes, we're going to look at offense group robberies and the hour between 9 a.m. and 6 p.m. So daytime, basically. I'm going to use what is called a marker to group each different incident into one marker. So we need a background map, and this is how we define it. We can zoom, we can center it in a specific latitude, longitude. We're going to use a different background map here, this CartoDB position. I'm going to zoom in a little bit more, zoom start 13. Then for each point in our data frame, we will iterate over the rows. If we do that, we're going to get a tuple, which is basically two things, the index of the row and the actual row itself. The row itself has all the fields that the data frame has. We only need the latitude and the longitude. And for each one of them, we will create a marker object, which is a volume object. And we'll add that to our underlying map. And then just displaying that map, we're going to see how it looks like. So the gray background is this volume map feature here, and the blue one is the default color, I guess, of the markers. So we can zoom in, we can see here different parts of the city. See here, maybe the center, it looks a little bit busier. And this looks basically like a Google Map visualization. Maybe this is a little bit crowded, especially if you zoom out. So maybe you want to cluster things together and maybe give a color so that the more dense it is, or the more incidents have happened in a location, maybe the more red it is, for example. So to do that, again, we're going to use an underlying map. We'll create a marker cluster. Then we want to make sure that those latitude and longitude are not NA. I mean, above we drop NA, so this is not necessary, I would say. Then for each one of them, we'll create a marker as before, but we'll add that marker to this marker cluster object here. And then in the end, we're also going to add this marker cluster to the underlying map as well. So now when we look at the map, we have a collection of data points and just a number. So in this area, we have 35 incidents. In this area, we have 9. And if you zoom out, you'll see that this numbers update. So if you zoom totally out, that's the total number of incidents. Then if you go here, maybe we'll have a breakdown. So there are 6, there are 2 here. It's a bit more useful to read, and it's not as crowded as before. Cool.
I think this one's really amazing.
What do the colors mean?
All right, very interesting, right? Yeah. It kind of takes away
a range of values.
Looks like under 10 is green, between 10 and 100 is yellow.
Yeah.
And what is it, orange when you zoom out more?
Maybe 100, red.
Over 100 is the red.
Yeah.
It's about heat bubbles.
Yeah. Cool. Let's look at what is called a bubble map, which is basically a circle, and we can adjust the color as well as the size of a circle for different metrics. So we'll start with underlying map again. Then you'll see this often. We'll have what is called a number or a color for different levels. So somehow we need to classify what color to assign to our circles. And to do that, we need to do that based on a value. So for example, if we're more than or less than 12 incidents in a region, then we'll just give it a green color. If we're more than 12 incidents, we're going to give it a dark red.
I was surprised to see them use red and green, because that's kind of, I mean, that's, you just don't do that for color blindness. You use more colors that have different contrasts.
Mm-hmm. So then we're going to iterate over the same information again, the same data frame or geodata frame, and we'll create what is called this circle object, and let's see what is it made of. It has 3 arguments: location, radius, and color. The location is the center of each circle, so we need the latitude and the longitude from our data frame. Radius in this case, we're just making the same equal radius. We can adjust this as well if we want. And
Yeah,
for
so you
color-
could actually make that, can you specify a column in the data frame for that so that the circle, so the circles actually scale themselves?
Yep, we'll do that in the exercise, yep. And for the color, we're specifying the hour. Oh, sorry, the hour is if it's before noon or after noon. It's not if it was 12 incidents. So if the hour is before 12, we're gonna give it a green. If the hour is after noon, it's gonna give it a red. Let's look at it. They only have all the circles have the same radius. It's just the color tells you the time of the day. So green is in the morning, red is afternoon or evening. You see here, there's a collection of them in the evening. Cool. Another visualization feature that Folium has is a heat map. So let's see how that looks like. That's very easy to call. We don't have to iterate over different data points. It does that for us. We just have to give the underlying data, and we have to specify, it is crimes data frame. We have to specify the latitude and the longitude. And we just specify the radius. That this basically changes the color of how close data points need to be together for the color to change. So just one line, and let's look at it. So red means a higher number, but there's no legend here that tells you what that exactly means. So this reminds me a little bit of that cluster that we saw above, but this is more spread out, I would say. And again, this is not as clear when you zoom in. Maybe if you fully zoom in, you get the latitude and longitude of each location. But when you zoom out, you see they're starting to merge a little bit, and maybe that's not that accurate, right? Because it looks like it's interpolating in between.
Are there any units for the radius?
We can look at it. Folium heat map. Let's radius of each circle in pixels. No, that's for circle pattern. Should be somewhere in the beginning. Heat map. Okay. Radius of each point in the heat map, but doesn't really tell me how that is calculated, or
Doesn't give a unit.
yeah, I don't see any here. I'm not sure. So radius control the smoothness of the heat map. Higher values make the heat map look smoother. So just a smoothness effect, I guess. Okay, another one is choropleth. We're gonna look at different districts, police districts in this case. We will need an actual shapefile for this. We can't just rely on latitude and longitude anymore. We need a region for each police district. In this case, we're only gonna extract the district field and the geometry field. We're also gonna set our index to district, so that now we just have our index is the district of the city, and the geometry is a polygon or multi-polygon. We look at the unique districts, how many we have, how many records we have for, or how many incidents we have for each district. D4, not sure what that is, B2, A1, C11, B3. So let's see how can we visualize that. We can create a background map. Then this new object, choropleth, where first of all we have to specify what is the underlying region, and they are under districts. And this is using this geo interface, but that basically what that does is it converts this multi-polygon that we saw here to what is called GeoJSON format that Folium expects. So that actually happens if you call this attribute here, which I found it interesting. For our data, which means the color of the region, we're going to use this plot dictionary, which is basically a value counts for each region. Key on, we'll look at that, we'll look at that, we'll look at that. Let's look at the map first, I would say, before this all features make sense. So each area is a police district, and the color, if you look at the incident legend here, is based on how many incidents we have per district. So yellow is low, blue is high. And you can zoom in as well if you want. So the geodata, we use this geo interface to convert this geometry field to a GeoJSON file. We use the number of incidents to color code its geographical area. And then when we convert that information to GeoJSON, internally there's a features and there's an ID field as well. That's why, or key, that's why we use the feature ID. Field color, let's go back. So that was the key on. Field color was yellow, green, blue, a scale of yellow, green, blue. A legend name, that's very important, and add it to our underlying map. And that's it. So now we have it broken down by region and number of incidents. Great, let's look at the exercise real quick where we change the size and the shape of each circle and the color. And we're out of time as well, so try to be quick here. So we're going to look at a completely different data set. This was a very interesting one of Japan, and we're going to look at earthquake data from Japan. And also we're going to look at population density and see if we can make some kind of suggestion of, which areas are basically but which areas would you invest the most, especially if there's a lot of people living there that are also prone to earthquakes. So which areas are both high in population density and prone to earthquakes? That's what we're looking for. Okay. So we'll import pandas, GeoPandas, Folium, Choropleth. That allows us to visualize regions, heat map as well, that we saw above. Looks like there was an issue with Kaggle notebooks and maps displaying in web browsers, so that's why they're using this embed map where they use the IPython display iframe, they save it as a file, the map, and then they actually display it again. For me, I didn't have any issues, but I guess that's for other browsers maybe. So we'll look at displayed boundaries shapefile, and you can see there's a length, some information about it, and what we're interested in is this geometry information here. So I'm just looking at one of them. It's a line string. If I look at the coordinate of it, it's a coordinate sequence object. I can convert that to a list, and now I have the data points that make up this line here. You can see the individual latitude, longitude. So that is doing all those pieces of information here. From the geometry, is extracting the coordinates, it's converting it to a list, it's flipping the latitude and longitude simply because our visualization isn't in that way. So that's creating the coordinates, and it's dropping the underlying geometry field. So basically we dropped the previous geometry field here, and we created this coordinate field here. That Folium needs to visualize. So that's our tectonic plates information. Let's get our earthquake information. That is, looks like a time series. So we have a daytime, latitude, longitude of the earthquake, the depth of the earthquake from the surface, the magnitude of it. The higher this is, the worse it is, and an event ID. And let's look at visualizing where the tectonic plates are, as well as where the earthquakes are happening. So let's use an underlying map, and for each of our tectonic plates data set. Let's create what is called a polyline. That's a new construct for us. We will use the coordinate field, and we're going to give it a weight. Probably this is the thickness of the line. I'm going to give it a black color. So that will be our tectonic plates data set. And on top of that, we'll add a heat map of the earthquakes. The radius is 15. And the color will be if a lot of earthquakes happen closer to each other. So let me zoom out a little bit. So in black here, you see the tectonic plates, and you can see them around the world. And in this heat map, you can see that most earthquakes happen where the tectonic plates meet. And let's go to Japan real quick. So Japan, you can see here, has a lot of earthquake incidents over time. Zoom out again a little bit, because there are other areas interesting as well, especially South America, west of US, Southern Europe as well here. So that's this area here around Thailand and Australia. Okay, so let's see. Is there any relationship between earthquake depth and proximity to a plate boundary? So the deeper an earthquake is, usually the less, so assuming the same magnitude, if you had an earthquake very close to the surface of the earth versus one that's very deep, the one that's very close to the surface of the earth is more catastrophic for us. So we want to see how deep these earthquakes are, and if there's any relationship between how deep they are and how close they are to a tectonic plate. So that's our original data set. I just created a new color code here for the magnitude. I said if it's less than 5 Richter, and the scale for earthquakes, give it a green, less than 6 yellow, less than 7 orange. If it's more than 7, give it red. And the same information about the boundaries for our tectonic plates. And now create a circle, let me zoom a little bit more, where the location is the latitude and longitude for each earthquake. The radius for me will be the depth. So the wider it is, the deeper it is. And the color will be the magnitude. And let's visualize that. So color is magnitude. So red is more than 7 Richters, and orange is between 6 and 7, and so forth. And if you look at the size to me looks more or less the same. Maybe I need to figure out the scale, because maybe they're so close to each other, the depths, that this map here is making them look very similar to each other. So let's look at maybe around the world, maybe it's what is going on. You can see here, we have a lot of oranges around here, some red ones in Turkey, some orange ones around here as well, and red ones. Okay, now let's visualize the depth a little bit. If it's less than 50 units, I think this is kilometers, I'll give it reds. If it's less than 70, orange. And if the deeper it is, the more neutral color, I'll give it like green, for example, meaning it's less catastrophic for us. So now I'm keeping the radius the same, but the color now is based on the depth and not on the magnitude. And if it's green, that means it's deep underground. If it's red, it means that it's very close to the surface. So many of them are actually very close to the surface. And that's why they're so catastrophic here. Let's look in Japan, especially here. You see here, they're very close to the surface. Someone here, many of them here are deep underwater, underground. But a lot of them here are very, very close to the surface, which is very bad. You can look at that across the world as well. Then the last thing we're going to look at is different counties or prefectures in Japan. We're going to see where most people live and how does that correlate with different earthquake incidents. So for that, we'll import this boundaries shapefile from Japan. Let's look at a few records. We're going to set the index as well. So it just has one field and the index, which is a multi-polygon. Also going to read the population information from Japan. Again, prefecture and population. It's important that they have the same index. And then what we're going to do is we will use the geometry field from our first data frame here. We'll convert that to CRS 32654, which is more accurate for calculating area. We'll pick out the area, convert it to square kilometers, give it a name, and we'll also join it with a population on our index. So let's see how that looks like. So now we have two fields, population and area in square kilometers. That means that we can create now a density. So what is the population over the square area? And just looking at 5 records, we have Tokyo, Osaka here, Kanagawa, and you can see the density. So the higher the density, the more people live there per square kilometer. Great. So then we want to visualize a basic map, and then we want to visualize each different region using our density information in this yellow, green, blue scale. So basically, we want to visualize the population density in different regions. All right. So most of them have this yellowish color. And let's look at, there's a legend here somewhere. There's a mountain legend. Yep. So the legend is yellow in this 71 residents per square kilometer, all the way to blue to 7,000 residents per square kilometer. Let's see where the busy ones are. So capital, obviously Tokyo, is very dense. The next region next to it as well as dense, and this Osaka region as well as very dense. And I actually look at the different regions in Japan, and you can see that different names here. And the next thing we're going to look at is real quick is, again, the same population density, but in this case, we will add a circle for each earthquake. And the radius now will be the magnitude to the power 5. This, looking at the solution, gave a very good estimate, or much better user-friendly size. For the color, again, we're going to look at the magnitude. So both the scale, both the radius and the color are magnitude related. So the wider the circle is, the higher the magnitude, and the more red it is, the more higher the magnitude, or more dangerous for us. So let's look at that. So now we have our population density as well as these circles. So the smaller the circle, and maybe green or yellow, that's smaller magnitude. Oops, sorry. The bigger ones, like for example, this one here, the more devastating it is and the more higher magnitude it is. You can zoom out around the world to see if there's any patterns here, but you can see Japan is there. You can see them around Australia here, Southern Europe, Atlantic, and then the coast here, the West Coast, North and South America. Apparently a lot of them here. Last map. And so what are we looking at here? We're looking at magnitude being greater or 6.5, we're giving it red. I think this is a solution one. The only new thing for me was here that You can actually specify what is called a pop-up in the map. So when you click on an item, you can actually get a pop-up. In this case, we're going to get the magnitude as well as the date, time, year for the incident. So you can make your map a little bit more interactive. So this is using a slightly different color scale. It's just using red and green if the magnitude is more than 6.5 or not. But it's using this feature that if you click on now in a circle at the boundary, you get the magnitude, which is 6.8, and the year. So click on this one. This is 6.3, 1993. Let's look at this big one here. To click on the boundary exactly, that's a 9.1. That's a big one. To 2011. So you can do this for any other one around the world. Cool. That's all I had for the first 3 units. Sorry it took longer than expected, but this is the different earthquakes that are taking place around the world. Questions or feedback while I transfer control over to Kathleen?
Okay, so you can see my screen.
Yes.
Okay, so this this section will be talking about geocoding and joining table joins. So you can actually just input a location, and it doesn't even have to be a perfect location, and get the geocodes for it, and then you can do all the stuff that George was talking about and more. So to use the geocoder, you provide the name or address as a Python string and the name of the provider. So they are using the OpenStreetMap nominatum geocoder. And that'll give you a geometry column that we've been seeing in the other geo data frames, and the address improved if necessary. So this one here is just the Great Pyramid of Giza and the provider, and then it gives you the point data, the geometry as point data with a long and Latin, and this new address. So the result is a data frame with just 1 row and 2 columns. And you can turn that into a, you can pull the Latin long out of it. So this will read, they're going to work with university data in Europe, and here's the CSV file read into a pandas data frame. And it's just the name here. So there's no geolocation data on it. And this function here will take, it uses try and except in case there's missing information or that it can't find something. The point becomes the, uses the function geocode and pulls out the geometry, and then from the first record, but there's the first row of the data frame, and it returns a series, a pandas series of from this dictionary, the Latin long, and let me see. And the geometry is a point. So this is returning a series with these 3 items in it. And then the universities, the lat, the long, and the geometry pick up that data when the function is applied. And this shows you that there are 91% of the universities they were able to get the geocodes for, and this is the resulting data frame. So to visualize it, you create the background map with Folium, and then use the iterator to pull up for each row and create a marker from the Latin long, and the name is going to be on a pop-up, and you add it to the background map and display it. So these are the universities in the data set. You can see there are some that are not in Europe.
Maybe they migrated.
Actually, they might have been, like, what do you call it? The additional, what do you call it?
The geocoding, I think maybe it didn't work properly because we just gave a name, right? We didn't give anything else.
So you think they're not like satellite
Maybe
versions of the university?
No, I think it's just the geocoding is happening.
So, and then if you the pop up here, you can see that it uses the it's the encoding is not changed. So, like this is Sorbonne, Universität Catholique in Leuven.
Yeah, we talked about this last time. That's an interesting problem.
Yeah. So then for table joins, this is pretty cool. It's really pretty simple considering what it's doing. So we talked about in the pandas about joins and merging, and this is an attribute join. So the best thing to do with geodata frames is a merge. So here's a data set with the European boundaries. They're multi-polygons, the geometry, and then the statistics, European statistics, with the same note that they have the same index. So Russia, Norway, Sweden, Russia, Norway, Sweden. And you do an attribute join. So all you need to do is take the boundaries and merge it with the stats on name. And this is what you get. That's pretty neat. But the spatial join is really cool. You have the excuse me. You can join a match of the university to its country. So you do a GeoPandas spatial join with universities in Europe, and then you look at the results. They located 91 universities. 86 of those were located in Europe in 15 different countries. And this is the resulting data frame. So it's got the median estimate, the population estimate. It was matched on name, and these are the geometry points of the universities. So look at the exercises for this. We pull in the normal things. And this is so here they're talking about California and where they're going to place these Starbucks Reserve roasteries, which are like super Starbucks, and as if there's not enough of that sort of thing. And you pull in Folium, the stuff we've been working with before. And this embedding function that George mentioned. The Starbucks is loaded into a pandas data frame read from a CSV file. It's got a store number, a name, an address, the city, and the long and lat. And there are 2,800 records, the 6 columns. Not all of the locations, not all of the stores have locations. So they said that Berkeley is missing. And these are the 5 rows for Berkeley. You can see that they are missing their geolocations. And here, this shows you that the some of the columns with nulls are 5. And since there are only 5, or Berkeley are missing 5, they have to be the same ones. So this fills in the Latin long by geocoding the Berkeley, so you can see with if you the point is created from geocode given the address in the data frame, and you pull out the row, the longitude and the latitude from the point X and the point Y and return it, and you apply that to the Starbucks data, and then you're able to geocode the Berkeley data. So these are the Berkeley locations. Now you can see that they have their geolocations, the points, and we can create a map. So the folium map is the background, and adding markers for each of the Berkeley locations, and with the pop-up being the store name. Okay, good. Earlier I had run out of my allotted use of mapping soft of OpenStreetMap just before we were starting. So these are the locations of the stores, and you can see the name of the store from the pop-up. If you zoom in a little bit, I don't know
just a subset, or is it the entire data set?
This is just the Berkeley, yeah. Considering only the 5 locations, how many of the locations seem potentially correct? I don't know Berkeley. I don't know that area. I thought a lot of them looked pretty far. I thought these looked pretty far from Berkeley, but they say that they're all correct. And then if you have data from other sources, other information, you can consolidate it into a data frame. So they're picking up a geolocated file called the county boundaries. And this is what this looks like. It's got a geo ID, the name of the county, the area in square kilometers, and the geometry file, which are polygons and multi-polygons. And then creating 3 data frames from the California population. California high earners are people with income of at least 150,000, the number of households with at least 150,000 a year, and the median age for each county. So these this cell reads all those into Pandas data frames, and you can see the population. You can see then that the geocode is the same as county geocodes. So in the next, what you want to do is join that data with the California's county data and creating California stats. So my solution was merging merging each one based on GeoID. And I like their solution better, which is to join the auxiliary data,
Mhm.
reset the index, and then merge it. And if you look at data frame join, that's a better way of doing it. And if you don't specify what you're going to merge it on, it does an intersection of the columns and the data frames and the series that you're working with. And so if they all have only, for instance, here, the GeoID in common, then you don't need to put the on. It will figure that out for you. Or if you had more than one column, it would figure it out. So now you're going to compute the density as a new column in the California stats. And to look at that, you can see the density is there.
Mhm.
Then they just ask, this is not so much a geospatial question, but they want to know where they need enough households that making enough money. They want younger people and they need the density. But they also say you could, they need at least one of these characteristics, that at least 500,000 households are making over 150K. The medium age is even younger, or the density of inhabitants is higher. So these are the selected counties. I did it in two stages, selecting the counties that met the first criteria, and then the counties that met the second, where there was at least one of the other characteristics. So the number of counties before the filtering was 58. You got down to 6 with the first characteristics, and then down to 3. And let's see this one. These are the actual stores that fit those characteristics. And the number of stores. Let's see. It's 1043 that fit those characteristics.
So the
Then
cool
you-
thing was they did a spatial join, right? They did an S join there.
Yes. So these are the selected counties in the Starbucks spatial. And they joined them.
So the spatial join is that you have locations and you have regions, and the spatial join is that if a location belongs to a region, it will be mapped or matched with that region, right? If it doesn't fall inside a given region, then it won't be matched or it
Right.
won't be joined.
It doesn't come out of the join.
Yeah, the spatial join was new to me. I think the examples they used were all joining points with polygons. I was wondering if there were any other combinations that could be joined, if anybody knows.
I saw something called overlay, which had a GeoPandas, and it allows you to do unions, intersections, all kinds of set functions. I
So
think
adding 2 polygons and finding the intersection.
Yeah. So in the next session, or the next section, you can see a union of bubbles.
So when you do the spatial join, one of the data set has to be a region or multi-polygon or a polygon. Can it be anything else? Can it be like a line string or point?
Point.
Can you join points with points? I mean, that would be very,
Hmm.
you know, I mean, that means that what, the points overlap exactly that it belongs to. Maybe you want to give it like a buffer or something, like if they're within a given region.
So there is a buffer function, which, which then becomes a polygon.
Right.
Yeah,
Yeah.
It might be
region.
useful to be able to join line strings with polygons, though. Like, what counties does a certain highway go through or something?
Yeah.
Hmm.
Should we look? Well, it's pretty late, but that's certainly worth looking into. So the number of stores, so then visualizing these store locations, again, a folium map, and putting them on with the store name as markers. And this doesn't look right.
I think that's the base map. Later on, you add the population density.
No, but this is Berkeley locations, and it should be the selected store locations.
Hmm.
So that, yeah.
I think you passed it. Scroll up a little bit. Yeah.
I had, it's not displaying it.
Maybe.
So I think I ran into the same problem when I was doing the exercise. And I think if you have too many markers, it has a problem, because I think I copied the same code for question 6 as question 2, and it wouldn't display until I reduced the number of markers below a certain amount.
So maybe the next.
So it might be.
No, I take that back. It wouldn't display with the pop-ups, but if I got rid of the pop-up argument and just had it display unlabeled markers, that actually worked.
It's weird because pop-ups are like on demand, right? When you click on them, they're not always displayed.
Right.
Yeah, but they have to.
I think you kept the pop-ups.
Yeah, you're right. I commented the wrong one.
There you go.
No, it's still not.
Scroll up. There you go.
Yeah.
Where they go? All right.
Yeah, for whatever reason, I got the same result where it just didn't display with the pop-up.
Good.
But the marker cluster thing, I think, helps you overcome that. I think it can handle more data.
Okay. I have trouble also scrolling through these maps and scrolling through my notebook.
Yeah. Too many scroll bars.
Yeah. So. Yeah, so there's a lot of them. Interesting. Okay, so. Okay, so that's it for the joins and the geocoding. And the next one is proximity analysis. Is there any questions or anything on that?
Don't see any on the chat.
Okay. So proximity analysis, that's how you tell whether something, the distance between points on the map, and select all the points within a radius of a feature. So they're going to work with toxic chemicals in Philadelphia. And the releases is a shapefile. So it's going to be read into a GeoPandas data frame. And it's, these are in Philadelphia, and it has longitude and latitude and the chemical that was spilled. And the unit of measure, the chemical, the total release, and then the geometry. So it's a GeoPandas data frame. These are stations of air quality monitoring, and it's also a shapefile. It's got the site name, its address, black carb, I don't know what that means. All this technical data, and maybe whether it's metropolitan or not, and the latitude, longitude, and the geometry. So to measure the distance, first off, you need, of course, to be in the same CRS. These are in Epsg 2272. And this shows you the recent releases. Looking at the location 360, measuring the distance from the stations, and to this recent release, and that's just distance. And this shows you the distances from the recent, from that row to each of the 12 stations. So using those, you can obtain statistics like the mean distance to each station, the mean across to all the stations. And you can get the closest station using the distance min, and the location of the station that had that minimum distance, and that for this one is Penrose Ferry Road. So another thing is creating buffers around points. So you might want to, will certainly be interested in what's going on around a release. So to do that, it's very simple. You just go to the geometry and put the buffer and make sure your units of measure are correct given the CRS you're working with. So this one is measured in feet, and 2 miles is 2 times 5280. And this gives you a 2 mile buffer for each of the stations. Using Folium JSON, you can plot the polygons on a map. You have to convert, but to do that, you need to convert to the EPSG 4326 or some other one that is plottable. And you create the basic map. The location here is probably a central part of Philadelphia. And it's doing a heat map, adding that to the basic one, and the markers. They don't have pop-ups. So plot each polygon on the map using the GeoJSON, adding that to the map, and then plotting the map. So these are.
So each marker is a station, and the heat map is from the releases,
Yes.
toxic releases. Okay. So there's a huge toxic release in the upper right part of the map that's not near a station there.
This one here.
And the red one.
Here, yeah.
Yeah. So that's not within a 2-mile radius of a monitoring station.
Right. This is also a big one. That's
Yes.
not.
If you double click, it will zoom in for you, Kathleen. If you double click somewhere within the map.
Yeah, I'm trying not to double click too.
There's a huge, yeah, okay. There's some interesting one, really, what the 2 stations are. Okay, but they're interesting overlay of information, I would say.
This looks bad. This is definitely bad.
That's definitely bad, yeah.
So to test if a toxic release occurred within 2 miles of any monitoring station, you could run 12 different tests for each of them, but a better way is to create a multi-polygon using a unary union attribute. So you create, they call it my union, the 2-mile buffer, which is what this was up here, this 2-mile buffer, just by with that simple statement. And now you've got that all, and instead of separate regions, it's one large object. And this is what it looks like. So that's the union of those buffers. And then does the union contain that that one they were talking about before, on row 360, using its geometry? And it does. It does not contain the one 358. So yeah. So were there any questions on that, or?
I don't see it in the chat.
Okay. So the exercises now here are talking about, in New York City, there are accidents, and how close those accidents, those crash collisions, are to hospitals, and where you might want to place a new hospital. So importing the usual stuff, embedding, creating that function. Collisions is a shape file, and it contains the date, time, where it happened in terms of the borough, the zip code, the geolocations. And this location it's not a geometry. This is just combining the Latin long into a pair. Was it on the street? Was there cross street? Was it off street? And the different contributors to it. So if it was only a single accident, somebody crashed into a building or a pole, then these would be or none. It's got a unique key, a vehicle type, and whether there were. So this one actually had a second party involved, but it was unspecified. But the others are none. There wasn't a third and fourth. And then there's the geometry point. So that's the type of data they're working with. There were 262,000 of these. This is a heat map. They say to what type of map do you think would be most effective? I tried a couple of things. and landed on heat map, but I don't see that this is particularly helpful. It basically says that everything all over is,
Okay, you need to adjust maybe that radius.
I did that.
Hmm.
I did that and it didn't make much difference. I could play around with it some more, but see, I think they started with radius 10. And I used,
Or Chris is saying maybe a cluster map where you have numbers instead of color.
oh, okay. Yeah. I had a problem just before the meeting where I was not allowed to make any more maps. So that's why I'm not redoing these. And now, since I didn't run all the cells, they're not working.
It's okay.
So then, okay, we're talking about hospitals, and you read in a shapefile with the hospitals, and here they have an ID, name, address, zip, facility type, facility name, capacity, beds, all this information, and the most important thing is the geometry, because they want to know, are the hospitals near there's 62 hospitals, and are they near where the crashes are happening? So this is a map of the hospitals. And so a folium map underneath, and the markers with pop-ups that have the name of the hospital. So
Interesting.
NYU Medical Center, New York Methodist Hospital, New York Hospital Center. So when was the closest hospital more than 10 kilometers away from what was going on? And so you create a 10-kilometer buffer from the hospital data, from the geometry attribute of the hospitals, and then a union of them to get that rather than to have them as separate buffers, and then a function that says whether something is in the buffer. It's just, does the union contain the row geometry? And then the collisions apply that function to each of the collisions, and outside the range is false, and then they want an outside range data frame, and that just drops the in buffer column. So the percentage of hospitals outside the range, excuse me, divided by the number of collisions, there are over 15% are outside the range of the hospitals. So then make a recommendation about where to put the best hospital. And so it's the hospital with the minimum distance. So let's see, the geometry of the hospitals, distance from the collisions that would have a minimum distance, and return that hospital. So this is their solution. The best place to put the hospital is Calvary. The best hospital outside the range is Calvary Hospital. and which hospital is under the highest demand. So if you look at all of the collisions in the outside range data frame, which one is the most recommended? And the solution for that was picking the one that the best hospital with the highest value counts. And that turned out to be Jamaica Hospital Medical Center. And where should the city construct new ones? So they created a map with the coverage based on the hospital geometry buffer. And they added a heat map with the things outside the range. And then they wanted you to just look at that map and kind of pick a point where you think would be the best place for a hospital. And they want to reduce the number that are out of range below 10%. So if you look kind of like what George was doing with the in the previous exercise, pick one here, maybe here.
Yep.
And then I put inserted those in this as the choices, and they give you the code to actually come up with whether it satisfies the under 10%. And these 2 points actually did.
Oh, cool.
So I was thinking the exercise was actually to sort of build something like this that would spit out the right answer, but they really just want you to use, the utility of the map that you can go through and just kind of pinpoint something by hand and then test it out. That was what they were trying to get you to do. So,
And those are your new 2 hospitals there with a marker?
Yeah.
You reduced the demand, right?
Yeah. Yeah.
Awesome.
And those, yeah. So that's proximity analysis.
Thanks. I like the last exercise. Very interesting, Kathleen.
Yeah, this just seems like you could do so much so easily with these simple. I mean, to create a buffer, to create all these with just a one attribute of the geometry, that is really incredible. So.
Awesome. Thank you, Kathleen. Really appreciate it.
Mm-hmm. You're welcome.
Comments, questions, feedback, friends. This was a very interesting topic. There was some chat here about heat maps and how can we better control the color or the smoothness. And I think we can control. There's no separate control. There's only one control for smoothness and color. So we're just trying to figure it out. How do we?
So the smoothness would be changing that variable that should control the smoothness. I mean, the data set we're looking at just didn't have enough. It was all one big blob of collisions.
I was wondering if you could elaborate on the issue that you were having earlier where the maps wouldn't display. You're limited to a certain number of API calls.
Yeah. So I've been working on it all day and playing around with it, and OpenStreetMap must have limitations on I actually joined. You can actually sign up for OpenStreetMap, and I don't think that would have made a difference. But I couldn't find it, didn't have time to find out what the limitations were. But a lot of free stuff is like that. If you use the requests over and over again, they want to keep it so that you're not doing massive amounts of data processing with it.
But you ran into those limits just in those Kaggle tutorials?
Yeah.
Wow.
Yeah, I was playing with it a lot all day. But then, so it's been like 2 hours and it refreshed. So I don't know if it's a limit per hour or what.
I wonder if there's a Python package that you can call without actually having this API limit. I was hoping maybe it'd be a Python package, but I don't know how big that Python package
has different backbones for the mapping, right? Like you can use OSM tiles, but you can also use tiles from other sources, I think.
Yes, I think so, because it said we use this one just so that you don't need to have a what do they see?
Go ahead.
So the name of the provider, to avoid having to provide an API key, we'll use the OpenStreetMap nominatum geocoder. But there are, others.
I suppose they did that. I remember one of the lessons had a where they imported the geocode function from a different library than you would in practice, right? Like they didn't import it directly from GeoPandas. They actually defined their own within the Kaggle Learn Tools environment, which I thought was perhaps just a way to give you the experience of calling this API on this particular data set without having to actually call the real API. I think that was in the geocoding section.
Most services have limits on the number that you can points that you can geocode or addresses that you can geocode. I think Google is 2,500 per day.
Yeah.
And there is one service that you can use is Texas A&M University, the University of Texas A&M. They have a group that specializes in geocoding, and I think there you can actually do unlimited. It's not as precise as other services. Also, the quality varies. For example, Google Maps is very good. Some of these others, I'm not sure how good they are.
Yeah, I've used Google Maps. I've used another service called Geocoder. I haven't used the Texas one, but yeah, this, especially Google Maps, you had I think it's 5,000 lookups free per day.
Actually, you can geocode from the shape files, from the Tiger shape files. You can do a street geocoding. You can program that and do some approximation, but I think that's what the Texas does. But
so the shape file has. I mean, if it has, what does the shape file have that would let you geocode something that didn't have location data in it?
Well, you have coordinates, so if you have streets, that kind of stuff. It can interpolate or extrapolate. I'm not sure exactly how it does it, but I have seen programs in SAS that do that.
I don't think you can use a shapefile. If I give you like a store name, right? Like Starbucks at Main Street. I don't know if the shapefile.
Well, the shapefiles include the streets. I mean, depending what kind of shapefiles are you talking about. There are many that have additional information. So I'm talking about the U.S. Census Bureau shapefiles. So some of those have streets and information, so you can extrapolate. I mean, you can try to get it from there.
So you're saying it depends how detailed your shapefile is.
Yeah,
The more
Yeah.
detailed it is, the more detailed questions you can, or addresses you can geocode.
Yeah, they have layers. There are different layers on the shapefiles. So I believe that some, there is that way of doing this. So
I just go Google Maps, to be honest. 5,000 calls a day, I'm good.
Uh,
And
uh,
even if you exceed them, they're not that expensive. Go
but
ahead.
it had to be I'm not sure how Google. Well, I guess they are. I guess they take. They go with a car around and they take pictures of every house. So I guess they get locations that way. But without that, I believe there's something called street geocoding. I think it's where it's based on shapefiles.
So OpenStreetMap kind of makes you think that there's something called Street Map that's not open.
I don't know.
Well, they can be open till a certain extent, that where they can, give you can maybe geocode certain number of addresses. But I doubt very much that they can geocode unlimited, because otherwise you could create your own service.
Yeah. Yeah.
So
It just amazes me that you can, you can do it at all, that there's that much information in there.
oh yeah, it's
It's a little bit creepy.
Very handy sometimes, though.
Mhm.
yeah, there's a way to do it also with Google Earth. So you get very cool maps if you can, plot certain areas with KML. You can put it on Google Map, and you see all those pictures that you were seeing over there. That kind of you can see in Google Map and zoom in, zoom out, and pretty cool.
Awesome. Cool. Thank you, friends. This was a very interesting session. Thank you, Kathleen. I really appreciate your help taking a deeper dive.
Thank you.
Spatial analysis. Thank you, friends, for sticking with us.
Good night.
So long.
Good night, everyone.
Good night, everyone. Hope to see you next week for our happy hour. And on Friday, we have another session followed by a Friendsgiving event, which you can check out on our meetup page. Have a good night again, and see you next week.